Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on the efficiency of transformer. So first, what is meant by efficiency? For any machine, the efficiency formula is same. The ratio of output to the input is known as the efficiency. Percentage efficiency equals to output by input into 100. Now, if you give some input to the any machine, you will get output and you will get some losses here. Now, here in case of transformer, input equals to output plus constant losses plus variable losses. In the transformer, the constant losses are here iron losses and copper losses. Apart from this iron losses and copper losses, there may be stray losses and dielectric losses. Now these are the negligible losses, so don't consider these losses. First, the main losses are iron losses and copper losses. Here copper losses are the variable losses and iron losses means core losses are the constant losses. Now here the efficiency equals to output by input equals to output plus losses. This is input into 100. This is percentage efficiency. Now here efficiency equals to output by output plus this constant losses plus variable losses. Now here constant losses means iron losses and copper losses. Efficiency equals to percentage efficiency equals to output by output plus iron losses plus copper losses into 100. Now here this output equals to kVA rating of the machine into cos phi divided by output equals kVA rating this one and cos kVA rating into cos phi plus W naught means iron losses this one and copper losses WSC. Now here W naught and WSC can be calculated. So W naught is how you will measure the iron losses. Iron losses can be measured from the open circuit test and copper losses can be measured with the short circuit test. So that I will explain in later. First I will explain iron losses, copper losses, stray losses and dielectric losses. So first, what are the different types of losses? So the following power losses may occur in the practical transformer. So first, iron losses. Iron losses, another name is the core losses. So these losses occur in the core only and because of the winding. So transformer having core and winding. So because of the winding, so copper losses occurs. Copper losses, another name is the I2R losses and stray losses and dielectric losses also occur in the transformer. Now here iron losses. First I will explain iron losses. Iron losses occur in the magnetic core only. So magnetic core of the transformer due to the alternating a magnetic flux through it. So flux flows when you give the AC supply to this transformer. So the current is flowing and this current set up the flux. So that flux flows in the defined path. So because of this flow of flux in the magnetic core, so iron losses occurs. So for this reason, these iron losses are called core losses. And now here we will represent always this one as a iron losses. So these are two losses here, eddy current losses and eddy current losses and hysteresis losses. So we already discussed about eddy current losses and hysteresis losses in DC generator, DC machine and induction motor. Same thing here. So first here hysteresis losses. What are the hysteresis losses? Hysteresis losses because of the reversal of magnetism. So that is because of reversal of magnetism in the core. So hysteresis losses equals to formula KH. This formula is also we already studied. So KH is the constant and B maximum is the flux density. power of 1.6, and F is the frequency and V is the volume of the core. And hysteresis losses can be minimized by using high grade material, that is silicon steel. Silicon steel material. Silicon steel material. Now here eddy current losses. Eddy current losses because of the eddy currents due to the interaction of conductor and magnetic field. So eddy currents produced because of that eddy currents, there may be a loss. That loss is known as eddy current loss. Here that loss formula Ke constant and B maximum flux density and square and frequency square and T thickness of the lamination square and V is the volume of the core. Here to reduce this eddy current losses, we will use laminated core. Core is made up of with laminated, and material used for this core is high grade silicon steel material. Now copper losses. So copper losses means iron losses. Now this power loss occur in the windings. So what are the windings here? We have primary winding N1, and this is the supply which is connected to the supply is known as the winding which is connected to the supply is known as the primary winding, and the winding which is connected to the load is known as the secondary winding. So winding having some resistance, because of this resistance it the winding, if they carry current, and there may be a loss. So there may be a power loss. Here the power loss in the transformer that occurs in the primary and secondary winding due to the ohmic resistance drop. That losses are the, so why we are calling these losses are copper losses, because these windings are made up of with copper, and this losses another name is the I square R losses. I square R losses means this is the power formula, and total losses in the transformer is power loss in the primary winding and power loss in the secondary winding. So here suppose this is the transformer primary winding and this is the secondary winding. This one is the core supply and this one is the load. So now here this primary winding turns are N1, primary winding turns are N2, this is V1 and this is E2, induced EMF E2 and induced EMF E1, and this resistance is R1 and this resistance is R2, this current is I1 and this current is I2. Now this is the symbolic representation of transformer. Now here power loss means I1 square, power loss in the primary winding. Primary copper losses are I1 square R1, and next secondary copper losses are I2 square into R2, I2 square into R2. Now addition of this total copper losses equals to here total copper losses equals to, so summation of sum of power loss in the primary winding that equals to I1 square R1 and power loss in the secondary winding I2 square R2. So these are the copper losses. Now next losses, stray losses. Stray losses means, so fraction of flux, there may be a leakage flux. What do you mean by leakage flux? Fraction of flux flows to the air gap. So there may be in the air gap, so flux, this complete flux links with the magnetic core, but there may be a air gap flux. That flux is known as the leakage flux. Because of this leakage flux, eddy currents produced in the conducting material or metallic parts. So because of that currents, there is a power loss. That power loss is known as a stray loss. So this is negligible loss. Now next, dielectric loss. So losses occurring in the insulating materials. So what are the insulating materials in the transformer? Now here oil, solid state insulation of the transformer. So because of power loss occurring in these materials, such type of losses are known as a dielectric losses. So dielectric loss is significant only if in the transformer working on high voltages. Now these two losses are negligible. So now total losses equals to, so now here what are the total losses equals to iron losses plus copper losses plus stray losses plus dielectric losses. So now here PE and P eddy current losses and hysteresis losses in the primary copper losses and secondary copper losses. So now stray losses and dielectric losses are negligible. How you will, so if you neglect this one, if you know this iron losses and copper losses, then you can easily determine the efficiency of transformer. Now here, how you will calculate this iron losses? Iron losses can be measured with the help of open circuit test. By conducting open circuit test, you can measure the iron losses, and by conducting the short circuit test, we can short circuit test on single phase transformer, we can measure this iron copper losses. So first, open circuit characteristics. Open circuit test on single phase transformer. So from this you will get the iron losses. So how you will perform this test? First one, this is the transformer. So transformer primary winding, this is the transformer secondary winding, and transformer core. So these two parallel lines indicates the transformer core. So this is the transformer. Suppose I am taking here 150 volts by 230 volts transformer, and a step up transformer I am taking a low voltage winding and high voltage winding. So this number of primary winding turns are less than number of secondary winding. So this is the transformer 115 volts low voltage and 230 volts. So I am taking this one. Now here, to conduct this test, I need, this is a V1 supply. So 115 volts. Total available supply in our laboratory 230 volts. And this is the auto transformer. Auto transformer main purpose is here, from the 230 volts supply, you can give to 115 volts to rated voltage we are giving here. So here from 0 to 230 we can change using auto transformer. This is the voltage across this to measure the rated voltage, and this is the watt meter. This watt meter is here LPF watt meter, and next here this is the ammeter. Ammeter is to measure the current. Now here secondary side is open circuit. So while conducting this test here, so first what are the conditions you need to observe here? So secondary side should be open. This secondary terminal should be open, and rated voltage, if this rated voltage is 150, rated voltage should be applied on primary. And next here LPF watt meter we will use, LPF watt meter. And next this LPF watt meter reading indicates, W indicates, that is iron losses. And this here primary should be LV side, low voltage side, and secondary should be high voltages. So now here next condition, primary should be LV and secondary should be HP. So now how you will perform first? So first give the rated supply, rated voltage to this transformer primary winding 115 volts to this primary winding through this auto transformer from 0 to 150, changes gradually from 0 to 115 volts. So then this reading, this voltmeter shows the this rated voltage 115 volts, and you will get the current and this wattmeter reading. Now this wattmeter reading indicates the iron losses. So now this transformer always primary should be LV and low voltage, and secondary should be low voltage. And the first condition, secondary side open circuited, rated voltage should be applied on the primary side, and the wattmeter should be low LP of wattmeter, and the wattmeter reading is iron losses, and primary has a LV side, LV, and secondary has a HV, high voltage and low voltage. Now here from this test we will get the iron losses from the wattmeter. And next, open circuit test. So now here from this we will get the W0. So what is the main purpose of open circuit test and short circuit test? So now to determine the equivalent circuit parameters and regulation of the alternator, regulation of the transformer, and efficiency of the transformer. So first from this we can equivalent circuit parameters. What are the equivalent circuit parameters? First from this we will get the W0, I0, and I0 is this one, this is the W0, and this is the V0. Now here W0 equals to V1 I1 and cos phi. From this you will get the cos phi value, wattmeter reading by voltmeter reading into ammeter reading, and IW is a magnetizing current, that equals to I0 cos phi, and Im equals to I0 sin phi. Next, R0 equals to V1 by IW, and X0 equals to V1 by Im. So these are the equivalent circuit parameters. So from the open circuit test you can determine the equivalent circuit parameters and efficiency. Next, short circuit test on single phase transformer. So how you will perform? So for that, in the previous case, same thing here. Secondary side should be short circuit. See the difference between open circuit test and short circuited. Their rated current, rated voltage. Here they rated current we will apply. And next, wattmeter is here UPF wattmeter. This is the UPF wattmeter. Here rated current we will apply. In the previous case, rated voltage we applied. And this is the secondary terminals are short circuited. And next, this wattmeter reading W equals to copper losses. And next, primary as a HV and secondary as a LV. If suppose in the previous case 115 by 230 volts, but here this is 230 and this is the 115 volts. 230 by 115 volts transformer we will use. 230 should be connected to the supply and 115 is connected to the load side. Now see the procedure first. See the steps. First, secondary side should be short circuited and rated current. Here rated current is applied. And next, UPF wattmeter. This should be UPF wattmeter, not LPF wattmeter. And this UPF wattmeter reading is a copper loss. And next, primary as a high voltage and secondary as a low voltage. Now here, how you will calculate, what are the steps? First, from the 230 volt supply through the auto transformer, give the rated current to this single phase transformer, and after giving rated current, you will get the VSC and ISC short circuit, and VSC and WSC. This is the ISC. You will get the WSC, VSC, and ISC formulas. Now after that, so from this you can calculate the Z01 primary impedance refer to the primary, VSC by ISC, and next RS equals to WSC by ISC square. So from this you can determine the reactance refer to the primary, square root of Z01 square minus R01 square. Now in this way we will get the iron losses and copper losses. And after getting iron losses and copper losses, we can easily calculate the efficiency of the transformer. Not only efficiency, we can calculate the regulation of power, regulation of transformer, and equivalent resistance parameters we will determine. Now let us take one problem and then you will get some idea about this efficiency of transformer. A single phase transformer 200 by 400 volts 6 kVA transformer, that is 50 Hz single phase transformer, gave the following readings. OC test is this one. LV said 200 volts. 40 OC test results 200 volts, 0.8 amp and 80 watts. And SC test HV side and 25 volts and 10 amps, 90 watts, and determine the efficiency of the transformer at full load with 0.8 power factor. First, I will write the open circuit test results and short circuit test results. Open circuit test always conducted on, this is open circuit, this is a high voltage and this is the low voltage side. So OC test 200 volts, 0.8 and 80 watts. So these are the iron losses, W naught, and this one is the I naught and this one is the V1. Next, SC test, short circuit test, this one is a open circuit test, and this 25 volts, 10 amp and 90 watts. This is the copper loss, WSC, and this one is the ISC and this one is the VSC. Rated current we have given here, rated voltage is given at low voltage side and here at high voltage side, this one. For short circuit test, high voltage side is primary and low voltage side is this one. This is short circuited. Now here power factor cos phi equals to 0.8. And now the formula for efficiency equals to kVA rating into cos phi, kVA rating into cos phi plus W naught plus WSC into 100. Now here kVA rating into cos phi means this is the output and this one is the output and these are the losses, total losses. Now kVA rating is 6 kVA means 6000. So this one 6000, power factor is 0.8 and this is 0.8 and this one is a 0.8 and total 80 watts here and 90 watts here. Iron losses 80 watts and copper losses 90 watts. Now if you simplify this one, you will get the 96.5%. I hope all these things are clear to you. Efficiency, losses, open circuit test and short circuit test. Next, this problem. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.